what is it, May 10th,
Right.
the 6 o'clock class. Like I say, we went through this the other day, but it needs another go through. So I want to do it with you again. You had a chance to look at it. If you have any questions, while we're here. So let me just remind you that the whole idea of this is to break down glucose. Remember, glucose is a very stable molecule. It's not easy to have it react with anything. So we have to activate it. Remember, the way to do that is to add energy to the molecule. The more energy there is, the more reactive it will be. The less energy there is, the less reactive. Usually, you do that by adding heat. But you cannot add heat to a biological organism. So instead, we break down ATP to produce ADP. I gave you that formula on the board. And the extra phosphate transfers over to the glucose molecule, producing glucose 6-phosphate. You have to remember the numbering scheme, which again we did the other day. So that's your number 6 carbon. So glucose 6-phosphate, in transferring phosphate, we're also transferring a little bit of energy. So what that means is that glucose 6-phosphate has more energy than glucose does. Therefore, it's more reactive than glucose, which is the whole point. This is an activation step. It's being activated, the glucose molecule is being activated because it received phosphate. That means it received energy, more reactive. It's a kinase reaction. Kinase is an enzyme that transfers phosphate groups. And the whole thing is a phosphorylation reaction. Any questions on the first reaction? Okay. Second reaction is essentially changing the glucose molecule into a fructose molecule. But specifically, changing glucose 6-phosphate into fructose 6-phosphate. I told you in something off the record that that's done by moving that oxygen bond in glucose from the number 1 carbon down to the number 2. So in fructose, oxygen is linked to the number 2 carbon. Now again, you don't need to remember that. That was just simply information, background. The important point is isomerase enzyme is changing glucose 6-phosphate into fructose 6-phosphate. That's all we need. The reason for that is to free up the number 1 carbon to get the number 1 carbon out of the ring. Now we saw the reason for that in the next step. The next step is another phosphorylation reaction, transferring a phosphate again from ATP over to, this time, over to fructose 6-phosphate, forming fructose 1,6-diphosphate. So 2 phosphates, one on the number 1 carbon, one on the number 6 carbon. That's why we needed that second reaction, to get that number 1 carbon out of the ring. Because carbon in the ring are extremely stable. And they're not going to react with anything. So by getting the number 1 carbon out of the ring, now you can add phosphate to it. And the reason for the second phosphorylation reaction is symmetry. Because now you have a phosphate on both the left and on the right. That's your symmetry. So this is not an activation step, even though it's phosphorylation. But not all phosphorylations are activation. Some are, some aren't. So in this case, it simply puts a phosphate on each side, and that brings it to the fourth reaction, which is aldolase, the aldolase reaction. The aldolase enzyme breaks this molecule right down the middle. It breaks the 6-carbon fructose 1,6-diphosphate into 2 separate 3-carbon molecules. And remember my comment the other day, I was very specific about not saying it splits the molecule in half. If you say that, I'll mark it wrong. Because to split it in half means you're getting 2 equal halves, and you're not. You're getting this, and you're getting this. Those are different molecules. The reason is because that oxygen right there It has to go to one side or the other. It can't go to both. So anyhow, the autolysis reaction splits the 6-carbon fructose 1,6-diphosphate into 2 separate 3-carbon molecules. And I commented to you at the time, this is the first significant reaction because of 2 reasons. One is the point of no return. Up until fructose 1,6-diphosphate, you could go backwards without a lot of effort. It hasn't changed that much. But once you've done that reaction, the autolysis reaction, now it's changed quite a bit. So to go backwards from this point would take quite a lot more work than it did earlier. So again, I'm calling it the point of no return. Jenny, something?
Why does it have to break up?
It doesn't have to, it just does. That's part of the pathway.
And then that's the reason why it doesn't have to break up.
Well, we haven't, let me just keep going. We haven't gotten there yet. So anyhow, so the 4th step, first significant reaction is to split that molecule into 2 parts. And again, the point of no return. But the second reason it's important is because it's the first time we break a carbon-carbon bond. Now that is important. Because keep in mind that ultimately, all these carbons are going to be broken up and changed into carbon dioxide. There are 6 carbons, we're going to get 6 carbon dioxides. So we have to break all those bonds sooner or later. So this is the first time we do it. So again, the first time we break a carbon-carbon bond, that's why it's the first significant reaction. So it gives us 2 different 3-carbon molecules. Remember, I believe on your charts, the phosphates are not completely shown. So if you're missing something, please just kind of draw those in. And then the 5th reaction was something that is not shown on the chart, but have you draw an arrow. The arrow being drawn from this molecule down to this molecule. So this molecule, the dihydroxyacetone phosphate, changes into glyceraldehyde 3-phosphate. So the end of the 5th reaction, and that 5th reaction is another isomerase reaction. So at the end of the 5th reaction, this has changed into this. We now have 2 glyceraldehyde 3-phosphate molecules. So at the end of 5 reactions, we've had 2 kinase reactions, 2 isomerase reactions, and 1 autolysis reaction. At the end of 5 reactions, we have changed glucose into 2 separate glyceraldehyde 3-phosphates. So let me stop for breath right now. Any questions on those first 5 reactions? Are you pretty comfortable? Yeah.
Why couldn't the fructose 1,6-diphosphate
The question is, why couldn't the fructose 1,6-diphosphate change directly to glyceraldehyde 3-phosphate? The reason is because of that single oxygen. We can't get 2 of these straight because the oxygen is in the wrong place. So by splitting the molecule, we do have to get this and this. And then it requires isomerase at that point. It requires another enzyme to actually move this into this. So again, as the molecule stands now, the oxygen can only go to one place or the other. There's no possible way you can get 2 of the same molecule. It can't be done. Yes?
I just want to confirm, so there's 2 kinase reactions.
Yes. In here, and that might be the answer to your question, Janet, is we now have 2 of these. So everything from now on is doubled. Everything occurs twice. So every single reaction here is actually occurring twice, once for each glyceraldehyde. So the next step here involves NAD becoming NADH. That's a reduction step. Actually, as you saw, that is transferring an electron, actually. It doesn't look like it, but it actually is. Transferring an electron, NAD becoming NADH. Later, at some other time, is going to become 3 ATPs. But not here. Right here, we just have NADH. Actually, 2 of them. The next step is our first ATP forming step. Yeah. She's so shy. ATP forming step, ADP becomes ATP, so that's phosphorylation. So you're adding a phosphate, that means a kinase reaction. Kinase transfers phosphate groups. So we're getting ATP out of this, times 2, moving forward several steps. Doesn't make much difference. We have another ATP forming step. So grand total, well, and then times 2. So grand total of 4 ATPs minus the 2 that are formed up here. I'm sorry, not the formed. Minus the 2 that are used up here. We're losing 2 here. So your all-time grand total is only 2 for the entire pathway. And then that brings us to the end product, which is pyruvic acid. And we talked about that also. We talked about the whole thing. It looks like that's the end product, but it's not. This is the end product, even though there's one more reaction. And it's the end product because this next step is something that occurs quite often, reducing lactic acid. It's extremely common, but it doesn't go anywhere. It's a dead end. And in fact, the lactic acid will sooner or later turn back into pyruvic acid. So despite how it looks, pyruvic acid is the end product. So for something unusual for me, I was very, very specific about telling you what you need to know for this. And I'll go ahead and repeat that now. Number 1, you need to know the starting point and the ending point. The starting point is glucose, ending point, pyruvic acid. Number 2, you need to know those first 5 reactions. Because we must have spent almost an hour talking about those 5 reactions. I spent a long time on it. So know the 5 reactions, and by knowing, I don't mean structure. You don't have to know structure. That would be silly. But know the actual reaction. For example, reaction number 1, glucose changes into glucose 6-phosphate. Why? Because it's an activation step. Number 2, glucose 6-phosphate changes into fructose 6-phosphate. Again, why? Well, that frees up the number 1 carbon. See, that's the kind of thing. Know what the reaction is and know why it occurs. You don't have to draw structures. Number 3, know those 3 enzymes. So I spent, again, a long time talking about those. Kinase, isomerase, autolase, and know the functions. Number 4, know about NAD, NADH. We haven't talked about those too much yet, but we will be. Number 5, know the mathematics, and I just said that actually. We're producing 4 ATPs, but using up 2. So your net product is 2. Getting 2 ATPs out of it. And finally, know about lactic acid. That lactic acid is the reduced form of pyruvic acid. Pyruvic acid is the oxidized form of lactic acid. A lot of material, a lot of chemistry material. Any questions? Any questions except her? Okay, go ahead.
The coenzymes are the NADH.
Yeah, NAD, and not coenzymes, it's just one.
Okay.
NAD and NADH are different forms of the same enzyme.
Okay.
So I would not call those, I wouldn't mark it wrong, but
Okay.
I would not call those 2 separate enzymes,
Okay.
or coenzymes.
Okay.
Just different forms of the same thing.
You
It's
just
kind of like you come to school wearing different clothes. It's still you,
okay.
just different form.
Okay. You said we have 3 coenzymes that
We
we
haven't
should know?
gotten there.
Okay.
Anything else? Okay, well, I kind of closed down on Thursday last week. I mentioned to you that there were several problems here. I want to repeat those problems. One is, it's a lot of work for ending up with 2 pyruvic acids. I remember double, so we have 2 of those. And essentially, I remember saying, you can kind of pretend you glue those back together again. You're almost back where you started. Not quite, but almost back. So we haven't really simplified anything. That was one problem. Second problem was the mathematics. All that work for 2 ATPs. And the third problem is, no carbon dioxide. And the fourth problem is no oxygen. We're not breathing yet. So I made the comment to you, not meant to cheer you up, but just to tell you that there's another handout. No, I can't